lecture will deal with the forward converter. We are always talking about isolated converters. They are galvanic isolated from the main grid or from the unregulated supply, DC supply. There are obvious benefits with regards to the dimensions of the transformer. The switch mode power supplies are studied and are possible in different topologies. The first one that we studied is the flyback topology that is usually intended for the lower range of power outputs. The second very common topology is the forward converter that is also intended for a slightly higher power range. Wanting to derive the topology from the non-isolated DC-DC converters, we can say that the forward converter derives from the buck converter or the step-down converter. An important characteristic is that the forward converter uses the transformer in the proper way. That is, the power enters from the primary windings and in the same time is forwarded to the secondary winding. This is different from the flyback converter, in which the primary winding was storing energy during the on phase of the switch, and during the off phase of the switch, this energy was forwarded to the output. In this case, we have a continuous flow of energy when the switch is on. As a consequence, the forward converter, the transformer of the forward converter, is usually said that needs a large magnetizing inductance. We want a transformer that is ideal as much as possible, and since we have seen that an ideal transformer has infinity magnetizing inductance, we want a transformer that has a large magnetizing inductance. Also in this case, this is different from the flyback converter, where a large magnetizing inductance is not so much needed because we want to store energy in the transformer before giving this energy back to the load. The practical difference is that usually the flyback converter, the core of the transformer or the flyback converter, usually has a gap, has an air gap that allows to reduce the magnetizing inductance and allows to store more energy in the transformer. In the forward converter, on the other hand, there is no gap. We have just a magnetic core with the largest possible magnetizing inductance. The converter is usually oriented to higher power applications, since it doesn't need to store this energy, but there is this continuous kind of flow of energy. The power range is slightly larger. Typical power is around 300 watts. This number obviously depends on the technology, the devices, but this is the range that is actually used for these converters. It must also be said that both flyback, so-called asymmetric converters, they belong to the family of asymmetric topologies, because the current flow in the transformer is only in one direction. This means that we are exploiting the transformer only for the positive currents. In principle, the transformer can work with positive and negative currents up to the maximum positive current and minimum positive current and maximum negative current before the core saturates, before we reach a limit that depends on the size of the transformer. Since in these topologies we only work with currents that go from 0 to the maximum, we are in a certain way just using half of the transformer in terms of power efficiency and power transfer. Higher power applications and higher power topologies are the push-pull, the half-bridge, the full-bridge converters that are, however, named as symmetric topologies. In this case, the current flows in both directions in the transformer. We will now conduct the usual step-by-step derivation of the forward converter topology, starting from something that we know, that is, in this case, the step-down converter. On the top, we see the step-down converter as we know it. This is a not isolated DC to DC converter. First of all, we need to add the transformer. The transformer needs to be introduced where an AC voltage component is present. We cannot introduce a transformer here, because here the voltage is constant. The transformer does not work well. We cannot introduce a transformer in series. This is the constant input voltage, VI. This is not a good place for the input transformer, the isolating transformer. The good place for the transformer is here, where, thanks to this switch, we will have a variable voltage. Introducing the transformer, we get to this circuit. This circuit, as a transformer, there is the possibility of different number of thirds from the primary and the secondary windings, changing the input to output relation. In principle, we still understand which is the working principle. We yet understand which is the working principle of this forward converter. When the switch is on, we will have the voltage here. This voltage will provide energy to this LC tank that is storing energy and is filtering the DC component for the output. When the switch is off, this transformer is not working. The freewheeling diode will provide the current to the load, and we are getting the usual back relation. Please note that there is no storing of energy in the first phase. When the switch is on, this high voltage here is forwarded here, and we are just transferring energy from the primary, from the power supply to the load. This is different from the flyback, where when the switch was on, the current was ramping in the primary windings, and there was no energy flow on the load. Usually in the books or in various lectures, you read that this is a proper transformer, while for the flyback it is more common to indicate the isolated component like the composition of two coupled inductors. Keep changing the topology, we can switch the switch position. We can move the switch from the high side to the low side with obvious benefits in terms of driving without changing the functionality of the circuit. Is this the forward converter? Is this circuit working? The answer is no. The circuit is not working. Please note that during the on phase, when the switch is closed, the primary side of the transformer is just experiencing the input voltage. Vp is equal to Vi. When the switch is off, we just say that we need a constant current in these inductance that will freewheel through this diode. This means that the voltage here will be just the voltage drop on the diode, that is more or less 0. We can approximate this to 0. And since this is a transformer, if there is 0 voltage here, there will be 0 voltage on this other side. Now this means that the average value of the primary voltage is different from 0. It's much larger than 0. If we substitute this transformer with the proper model that has the magnetizing inductance and the ideal transformer, we just understand that this means that this magnetizing inductance keeps being charged. The flux into the transformer decreases at every pass of the switch, and in the end we saturate the core and the circuit cannot work. We need a topology that allows us to have an average voltage on the magnetizing inductor that is exactly 0. This is not working. Why? Because this diode, when this diode is on, the voltage here is 0. We then need to decouple this voltage from the secondary voltage. This is easily done introducing another diode here. In this case, during the off phase, even if the current is flowing through the diode, this freewheeling diode here, even if the current is flowing in this freewheeling diode like this diode is off. In this case, we can have this voltage that is negative. Hence, we can get a negative voltage for the primary side also. This improves some aspects, but it's still not functional. This is the so-called ideal forward converter. It has the proper input to output relation that we expect. This is the basic topology from which all the other topologies are derived, but still it does not work. Again, we can introduce the proper model for the transformer, and we substitute this transformer with an ideal transformer and the magnetizing inductance. Let's see. This is the circuit of the ideal forward converter that we said cannot work in this way. We need to analyze what happens for the magnetizing current, that is the current through Lm here, during the on phase and off phases of the switch. Okay, let's see the on phase. During the on phase, the switch is closed. There is a current flowing through the primary side of the transformer and also an increasing current in the magnetizing inductance. This current that flows into the transformer is reflected on the other side of the transformer, with causing this current that flows through this diode, charges the output LC tank, and provides current to the load. During the off phase, the switch is closed. In this scheme, we can also understand another aspect that is also interesting. We say that we want to have a very high magnetizing inductance. We understand here we understand why. Because we can imagine that there are two paths of current into the transformer. The first one is the current that is needed for the load. The current that goes through the magnetizing inductance is just lost current. It's not a problem of efficiency, because it's not that big problem with efficiency. because there is an inductance there is some stored energy that you can reuse. But in order to have maximum efficiency, this inductance should be infinity in order to avoid this current flow. However, returning back to our discussion regarding why this ideal forward converter cannot work in this way, we can study the off phase of the forward converter. When the switch is off, there is no current through the switch. We say that this freewheeling diode is conducting, hence the current on the load is dictated by the LC tank and the load. There is no current here. This diode is off. Since there is no current in the secondary of the transformer, there is no current in the primary of the transformer. This is an ideal transformer. And the magnetizing inductance that has been charged during the on phase of the switch has no way to continue to flow. We need something to let the magnetizing current flow and to discharge the core of the transformer. This is the point. During the on phase, we transfer a portion of energy to the load, but we store some energy in the magnetizing inductance. Before the next on phase of the switch, we need to discharge the core of the transformer, that is the magnetizing inductance. This operation is the reset of the transformer, or sometimes indicated as the reset of the transformer. As previously said, this problem is the reset of the transformer. There are many topologies that have been proposed to solve this issue. Please note that for a good design, the magnetizing inductance is quite small, hence you just need low power energy flow path to discharge this magnetizing inductance, but you need to discharge it. Otherwise, after a number of switches, this energy will become too large, and the transformer doesn't work anymore. Among the various topologies that have been proposed and are used to solve the problem, here we study the forward converter with a tertiary winding. This is a common choice that introduces a tertiary winding in the transformer, another winding, that is used to discharge the transformer during the off phase. Something similar, we have studied it for the flyback converter, when we studied how to recover the energy stored in the parasitic leakage inductance to the primary. The resulting circuit, that is the forward converter with tertiary winding, or the forward converter for brevity, is this one. We still have the output LC tank and the load, the freewheeling diode, the diode needed to decouple the secondary side from the load, the primary winding activated by the switch, and this further winding and with N3 turns that is connected to a diode that will work during the off phase to discharge the magnetizing inductance into the power supply. In this way, we are also recovering some of the energy that is stored in the magnetizing inductance, and we are improving the efficiency. We can now study the forward converter in order to understand its behavior and how it works, and possibly a way to design it. Let's start from the calculus of the output voltage as function of the input voltage and the duty cycle. On the top, we see the circuit. We will assume a continuous current mode, that is the current into output inductor is never zero. We will assume ideal components, that is on state voltage drop for the switch and the diodes are zero, and ideal commutations, that is switching time zero. A common way, a simple way to understand, to calculate the output voltage is to impose that in one switching period, the integral of the voltage applied to the output inductor is zero. Why this is true? This is true because if the integral of this voltage in one period is not zero, we will have an increasing current or decreasing current from one switch to the next. And this is not possible. We are assuming that we are in the regime condition. During the on period, when this switch is closed, we will have the primary voltage that is equal to Vi. As a consequence, the voltage here on the secondary winding will be N2 divided N1 multiplied Vi. This is the voltage here. This diode is on, let's say 0 voltage drop. Hence, the voltage drop on the inductor, VL, will be Vi multiplied N2 divided N1, that is the transformer ratio, minus Vo. During the off period, the switch will be off. The current will flow through this freewheeling diode. This voltage here is negative. In the end, we can say that since this freewheeling diode has a negligible voltage drop, this node is at 0 voltage, and the voltage drop on the inductor is just minus Vo. VL is equal minus Vo. The integral of VL in one period will then be N2 divided N1 multiplied Vi minus Vo multiplied T on minus Vo multiplied T off. Dividing by T and simplifying, we get that Vo, the output voltage, is proportional to the input voltage, proportional to the duty cycle, and proportional to the transformer ratio, N2 divided N1. This is exactly what we expected. We see that this derives from the step-down converter, from the back converter, whose constitutive relation is Vout is equal to Vi multiplied the duty cycle. We just add the transformer ratio, that is N2 divided N1. In a similar way, we can get the same result, stating similar to what has been done for the step-down converter. We can say that the output LC tank behaves like a filter that extracts the C component from the input voltage, that is Vo first here. And since Vo first is the N2 divided N1 multiplied Vi during the on phase and 0 during the off phase, the average of this Vo first will be exactly Vi multiplied N2 divided N1. This is also a very simple way to calculate the input to output relation for the forward converter. Since this calculation is more or less straightforward and we've done this more than once, we take this occasion to calculate the output voltage, introducing some more realistic assumptions. As an example, we can calculate the output voltage removing the hypothesis that the components are ideal, and for example, we can say that the diode voltage drop is not zero, but is equal, let's say, to VD. This is a rough assumption, but not so rough, since we know that the diode is more or less a constant voltage drop plus a ST component. But since the current is more or less the same in all the diodes, we can say that more or less all the diodes have the same voltage drop. In this case, we still integrate, we impose that the integral of the voltage on the output inductor is zero in one switching period. And the difference are simply that during the on phase, this switch is on, the primary voltage, let's say, is VI. This voltage here is VI multiplied N2 minus divided N1. And the voltage drop on the inductor is this voltage minus VD minus VO. During the off phase, the voltage drop is in this the voltage drop on the inductor will be equal to this voltage minus VO, but this voltage is minus VD. Yes, this is minus VD. The integral of the inductor voltage is then N2 divided N1 multiplied VI minus VD minus VO multiplied T on minus VO minus VD multiplied T off. This relation is correct. And substituting, dividing by capital T and substituting the duty cycle, we get the voltage drop, the input to output relation from this equation is this one. That is exactly the same as before, with the difference that there is this voltage drop on the diode that is subtracted. This is reasonable since the voltage drop at this point is just diminished by VD in both phases. This is one example on how we can improve our estimate of the output voltage. Another possibility, very simple one, is removing the hypothesis that this V on is equal 0. We can say that V on is different from 0. This would be very simple also, because the only difference would be that the primary voltage is not VI when the switch is on, but will be VI minus the on-state voltage drop. This voltage here would be VI minus the on-state voltage drop multiplied N2 divided N1, and you can conduct exactly the same calculations to get the input to output relation as a function of the duty cycle and including the on-state voltage drop on the diodes and on the MOSFET switching transistor. Let's say this is a technique that I'm explaining, but it can be improved in many ways. Once we are completely convinced that the input to output relation is what we studied, and we put an effort in understanding the output section of this forward converter, that is this region, let's try to understand the behavior of this section here that is slightly more complex, also because we inserted this tertiary winding to reset the current of the magnetizing inductance. There are many ways to study this transformer. Maybe the more simple way is introducing the model of the transformer explicitly, introducing the magnetizing inductance. We can introduce this three-winding transformer. This is an ideal transformer here with the coupling between primary, secondary, and tertiary winding. And there is one magnetizing inductance that takes into account the energizing of the core. This has been simply substituted. It has been simply substituted to this component here. We have the three voltages to the three windings, applied to the three windings, the primary, the secondary, and V3, that is the tertiary voltage. Please note that the direction of the tertiary voltage is downwards. The conventions for the currents that we used are IT1 entering through the dot, while IT3 and IT2 are exiting from the IT3 is also entering from the dot, and IT2 is exiting from the dot. The constitutive relation for this transformer is the following. The secondary voltage will be N2 divided N1 multiplied V1, that is the primary voltage. The secondary current will be, on the other hand, N2 divided N1 multiplied I1. For the tertiary winding, we have V3 that is equal to N3 divided N1 multiplied V1, and I3 will be minus N3 divided N1 multiplied I1. With these relations in mind, we can study the behavior of the circuit. Let's start studying the on phase of the switch. Yes.
Perché V3 nella slide precedente
Sì?
è concorde con la 1?
Perché in questa direzione, verso il basso. V3 in questa direzione sarà N3 su N1 per V1, però è la freccia che è girata. Capito?
E V1 dove è?
V1 è verso l'alto, è uguale a Vp. Se c'è una tensione qui, appare una tensione da quest'altro lato puntata verso il basso, che è proporzionale a N3 su N1, e una tensione da quest'altro lato puntata sempre verso l'alto, invece, che è proporzionale a N2 su N1. E i fili dipende da come li hai messi. Prendi due capi, li giri come ti pare dentro il circuito. Un altro.
Quindi quella V3 ha la freccia che sta lì, cioè non è riferimento alla 1, meno, no?
Il V3 è questa freccia qui. Se c'è una tensione positiva V1 che va di così, diciamo di così, V1 è uguale a Vp praticamente. V1 è uguale a Vp. V2 è uguale a Vs è in questa direzione e V3 va verso il basso. Perché te la trovi tutto al contrario?
Vado a fare l'equazione alla mano, non esce di 1 più V3 uguale a 0, quindi V uguale a 0. Cioè,
ah, tu dici, no, un attimo, ci devi mettere la decalatura di tensione su D3 e sul transistor. Non sono collegati questi due punti. Sono due punti differenti, quindi non puoi fare la maglia. La maglia deve tenere conto della tensione sul transistore e la tensione sul diodo D3. Sono degli altri fili praticamente. In realtà sul libro sul Mohan Underland questa IT3 è collegata qui proprio per dimostrare che è un altro filo che se ne va. Continuiamo. We can now study the behavior of the currents and voltages, and we will start from the on phase of the switch. This is the behavior of currents and voltages. The switch is on, hence we can say that here there is a short circuit. We are indicating the IT1, IT3, IT2 currents on the transformer, the magnetizing inductance, I1, that is the current from the power supply, and the switch current, ISW. Then we also have the inductor current, IL, and various voltages. During on phase, this is a short circuit. The primary voltage is VI. The secondary voltage will be Vs, and 2 divided N1 multiplied Vi, and this is positive here. This means that this D2 diode, the freewheeling diode, is off, because the voltage is positive here to here, and this is reverse biased. The current will flow through D1. If we want to focus on the tertiary winding, V3 will be N3 plus divided N1 multiplied Vi, and this is this voltage. This means that the diode voltage, positive versus the anode, will be equal to minus Vi plus V3, hence will be minus Vi multiplied with 1 plus N3 divided N1. First of all, this is negative. This means that this diode is off. Second thing that we will see in the following, this is higher than the supply voltage. The diode will need to sustain a voltage that is higher than the supply voltage. Another derivation, useful derivation from this negative current, voltage on the diode, the D3 diode, is that there is no IT3 current. This diode is off, IT3 is 0. We can then calculate the other currents and say that IT2 will be equal to the inductance current, IL. Once we know IT2, we can calculate IT1, that will be to IT2 multiplied N2 divided N1. This means that IT1 will be a function of IL. There is a direct flow of energy from the input to the output. This means that when the switch is on, this current is reflected here. There is more or less a straightforward direct current flow. Please note that if N2 is equal to N1, you are just saying that IT1 is equal to IL. The same current here and here. The magnetizing current cannot be calculated now, here, because it depends on the status of the core. However, there will be a magnetizing current in this direction, presumably, and the switch current will be the sum of the transistor current plus the magnetizing current. This means that the switch needs to sustain a current that is slightly larger than the load current, or the strict current that is required for the load, because we have a magnetizing current. And this also again tells us that it would be better to have a very large magnetizing inductance, because this means small magnetizing current and less overload of the transistor. This is why, for an efficient design, we see that the magnetizing inductance must be large, hence we can say that the magnetizing current is much smaller than the IT1. The IL current obviously will provide the charge to both the load and the output capacitor. In quantitative terms, during on phase, the voltages are constant through the device, through the circuit, while the currents are changing more or less. We then try to derive the behavior of the currents. We are then assuming that we are in the on phase, that is, the time belongs to the 0 to the t on time instant. We can say that the IT2 current increases because it is the IL current, and in this phase there is a positive voltage here that is larger than Vu, hence this inductance is being charged and the current increases. We can say that the IT2 as a function of time will begin from a value that is the minimum value, because we are at the beginning of the charging phase and we are saying that we are in continuous current mode. This means that this IT2 minimum is not 0, it's higher than 0. Plus a constant derivative that will depend on the time, divided by the L inductance and proportional to the voltage on the inductor that we calculated before. This can also be written as IL minimum plus the proportional inductive component. We can also calculate the magnetizing inductor current. It will be proportional to the primary voltage, that is Vi, proportional to the time and divided by the magnetizing inductance. The switch current will be the sum of IT1 plus IN. In this equation there is a trick, because we are assuming that at the beginning of the switching phase the magnetizing current is 0. That is, the transformer is completely reset. There is no current, no energy stored in the magnetizing inductance. Is this true? Yes, it is true. We will demonstrate this later. But also because if it is not true, the circuit cannot work. It works if we are able to reset the magnetizing inductor current to 0 after every switch of the transistor. This means that this equation is correct. The beginning current is 0. At t equal t on, when these currents are at its maximum, they will be defined by the previous equation, where instead of t, the time, we introduce t on. We can then plot voltage and current behavior in this graph. it is a bit complicated, but the circuit has a number of variables. This means that we need to study it in this way. In this graph, we are assuming that N2 is lower than N1. That is, the transformer is stepping down the voltage. And also we assume that N3 is larger than N1. This is not a very common assumption. Very often we have N3 equal to N1. In this phase, when the switch is on, we say that the magnetizing current in red will begin from 0 and then will increase linearly with a derivative that depends on the magnetizing inductance and the voltage, the supply voltage. We say that this current must be small. Then we have the IT1, the current at the primary, that also increases because it is proportional to the load current, and however will be scaled down or up by the N2 divided N1 ratio, that in this case says that the current in the primary is smaller. We do expect this more or less, yes, because if N2 is smaller than N1, we are stepping down the voltage. This means that the output voltage is small. If the power balance must be kept and the efficiency is 100%, on the output we will have small voltage, large current, and the primary current must be smaller than the output current. In orange, we will have the switch current that is slightly larger than IT1 current, and we have the load current, the inductance current, IT2, that starts from a minimum and reaches a maximum here. For the voltages, the primary voltage is VI, the secondary voltage will be scaled down by N2 divided N1. The transistor voltage is 0 because the transistor is on, and we just have the on-state voltage drop. V3 is positive and larger than VI, and the voltage drop on the diode is negative. The diode is reverse biased and is larger than VI.